Good to go? All right. Welcome to the survey strategy update session. My name is Federica Bianco. My pronouns are she, her. I'm LSST survey scientist. And we will also hear from Lynn Jones. Lynn Jones, do you want to introduce yourself?
Hi, I'm Lynn Jones. I'm the lead survey scheduling team scientist.
Thank you, Lynn. Together, we're going to present to you aspects of the survey strategy. Particularly, we are going to remind you of what the process for the survey strategy design is and what our most recent updates. Before I get to that, let me go through the usual reminders. This meeting has a code of conduct. We expect people to be respectful in all Rubin spaces. If you have witnessed or were subject to violations of the code of conduct, there are 3 contacts that you can reach out to. One is myself, Sandrine Thomas, and Jeff Carlin. Those are the email addresses. You can obviously also find us in person or on Slack. And if you need a reminder about what the code of conduct entails, there is a QR code and just some very basic rules of socialization. Remember that people can elect to put stickers on their badge that indicate their level of comfort with physical contact in a pandemic/post-pandemic world, and also social batteries that help gauge whether or not they may be able to engage in a conversation with you. If you're on Zoom, please keep yourself muted unless you are asked to unmute to speak. We have a Slack space. If you can ask questions there over Zoom, they are permanent, and so we may be able to answer them asynchronously if we don't get to ask them during the meeting. And I think that's all the reminders, so we can start with the session. So in this session, I will start with some background. I know that many of you have been to the survey strategy update session year after year here at the Rubin meeting and in all the other events where we run this kind of session. So this will be all news for many of you. But in order to make sure that everybody can follow, including the people who are new to Rubin and new to this meeting, we'll go into some details about how the survey design for Rubin works, what motivates the choices that we've made on how to design the survey strategy, and what are the players that organize and lead these efforts. We will give you a reminder about what a survey strategy altogether means and what LSST entails. LSST is not a single survey, but a collection of surveys. And we will review what the recommendation for the survey strategy was as of before the start of LSST. And then we'll focus on the most recent changes to that recommendation that are driven to a better understanding of the performance of the system and the decision to start LSST when we did, which enabled more rapid ramp up of science, but also entailed starting the survey when commissioning, some aspects of commissioning are still ongoing. And we will discuss some options for possible short-term additional modifications that may mitigate some of the current issues with the survey strategy. The spirit of this exercise dates back to when we wrote the LSST science book in 2009. And it was understood that even within the constraints that are set for the survey by the commitment to achieve the main scientific goals of the survey, cosmology, solar system, discovering the transient and variable universe, and galaxy science, galaxy and local volume science, there's still a lot of knobs that you can turn to collect the imagery in a specific way that will enable and support some science better versus other science. So it's a big exercise in optimization over the many, possibly the complete set of scientific goals that the astrophysical community has and that LSST can potentially achieve. Now, if we're trying to optimize over this very large community, which have very diverse interests, this can very rapidly become a competitive process, even what we dub a war. But we know that in a war, everybody loses. Some people lose everything. Every individual loses something. And together, we lose togetherness. And I think this motto was coined and adapted for the survey strategy by Phil. Thank you, Phil, for this legacy. And we still hold this, and this has been the bearing to decide how to run a community-driven, a community-oriented exercise of designing the survey of LSST. In practice, what that entails is ongoing and repeated interactions between the community and members of the observatory, where we hear from the community what are the science goals that we should achieve in the changing scientific landscape that we're designing the survey in. They provide ways of measuring the success that LSST would have for a certain science case if conducted in a specific way. And by the way, what that in practice means, like, how do I alternate over the images that LSST can take? Where do I point the telescope? What filter do I use? We make simulations of the catalog of observations that we could collect in 10 years based on different metrics, reward metrics that control the system. And we ask the community to measure the impact of the choices that we have made on their science case. We've been doing it repeatedly for over a decade. The process started roughly in 2014. And this is an exercise that is ongoing and will continue during the survey, because we are designing the survey to be flexible and be able to be optimized, responding to changing scientific priorities, better understanding of the system, et cetera, et cetera. So the community is really the main player in this exercise. And scientists from the community have contributed thousands of ways to measure the success of LSST. Many of those were written as memos, white papers, notes. Several of those were turned into peer-reviewed work. We have a astrophysical journal supplements dedicated issue for Rubin survey strategy, which is still accepting submissions, and today collects 30 community papers, 306 authors, 699 citations altogether. So really the protagonist of the story is the community that tells us how well would LSST do for a scientific goal if conducted in a specific way. The optimization process is handled by the Survey Cadence Optimization Committee. And you see all the members of the optimization committee here. I chair the committee. Lynn Jones and I are ex officio committee, so not voting members. And then I'm not going to read all the names, but here is the list of scientists that are currently staffing the committee. And we have a few of them here. Timo, Luis, and Kat are here, and you can ask them questions directly at any point. Also, we work very closely with the survey scheduling team, which is Lynn Jones, who's online, Peter Joachim, who's here, and Eric Nielsen, who's here, and you'll hear from later about how you can monitor the survey strategy, the survey ongoing as it happens. And they provide all the sort of technical aspects that support the SCOC. So they work with the SCOC on optimizing the survey strategy. They also have other responsibility, including chiefly writing and maintaining the brain algorithm of LSST, which is the scheduling software. Over the years, they've produced a variety of software that is both observatory-facing and community-facing. And the software that has enabled the community interaction with the SCOC and the participation in the optimization process, in particular, is folded into the Rubin SIM, and it's the OpSIM. This is the software that produces a catalog of observations that LSST could engage in, given certain rules for how to run the survey. And it's not really rules, it's a reward-based system, but I'm not going to go into those details. It's a catalog of observations that include the properties of the observations, such as where we pointed, what filter, what were the observing conditions, seeing, etc. And the metric analysis framework. So if you want to engage in the survey design process, this is the primary software that you would need to get familiar with, and would help you, would allow you to write a scientific case as a metric, which we then can measure a set of observation against. I want to discover kilonova, like Igor has done. I go to math, I produce a metric that measures how well I can discover kilonova, maybe how many I discover and get observed with certain minimum requirement. and that becomes a metric that the SCOC can use to see the success of a hypothetical LSST survey. So what I have here, right? So more practically, the way this works is we read your notes, we read your metrics, we have liaisons into each of the science collaboration that talk to the science collaboration. So we hear from you about how any of the simulations that we have produced is going, and maybe ideas for how to tweak the parameters of the simulation. Typically, we communicate with the community in a number of ways. We have a presence on community.lsst.org. We organize annual meetings, and we write PSTN, that stands for Project Science Team Notes. Those are the official recommendations that we make on how to run the survey. An important point is that this body recommends a survey strategy, doesn't decide the survey strategy. That is still something that the director does. So we make a recommendation to the director, and the director adapts, does not adopt, adopts, does not adopt, adapts, tweaks the survey strategy. And that process will be ongoing. The SCOC is a stable committee of the observatory. It will continue throughout the existence of the survey. We will continue to entertain the possibility of changing the survey strategy for the 10 years of the survey to improve the scientific throughput. Over the course of the 10 years during which this process has happened, we've made many changes to this perhaps naive initial plan for how to run LSST. Some of the key ones are here. The ones that I'm describing are the recommendation that the SCOC has made at the beginning of 2015. And it was a recommendation for how to start LSST about a year ahead of the start of the survey. We had finalized a footprint, which you can see in the graphic it's much more complicated than the original, I'm gonna say it again, perhaps naive footprint that had been designed. It's customized to make sure that we hit the low dust footprint that is of interest for extragalactic science in a specific way, the high dust footprint, which is of interest to galactic science in a different way with a different filter balance, perhaps different number of observations. And generally, when you see these maps, just to be entirely clear, you see colors corresponding to a number of visits on the sky. You see 5 dots in each of these maps. Those are the deep drilling fields, of which we have five extragalactic pointings that get observed 10 times as much as the white fast deep. We'll have details on how we run these observations later in the talk. You also may notice that on the left, you have a very uniform map in sort of 2-3 colors, green, yellow, and purple. On the right side, there are some blotches and patches. Those are actually due to the simulations that run the target of opportunity, where we do selected observing of areas of the sky where gravitational waves or perhaps solar system objects or neutrino triggers have been detected. We have finalized in 2015, we had come up with what we consider to be an optimal filter balance for the survey. So we have finalized a recommendation for the filter balance. Generally speaking, LSST observes with fewer images in U and G band and more images in the other filters. So you see the maps in different filters, G band at the top, I band, and Z band. See the number of observations that get taken in each. Those are optimized to achieve specific science goals. We also had recommended to take longer observations in the U band than in the other filters. All filters get 30-second observations. U band gets 38-second observation. That improves the image quality and moves us away from read noise in U band specifically, and that might be relevant when we talk about template collection later. LSST runs the cadence in a rolling fashion. So what you see here is a map of observations in 1 year. Because the sky is large and we want to cover all of it, but also we want to do time domain science, so we need observations to follow each other relatively rapidly on the same position in the sky. We adopt this survey where we observe more intensely a half of the sky on a given year, and then we alternate to the other half of the sky. So for every year pair, the survey is uniform across the sky. But that affords us a little higher cadence on the on season, which allows us to do much better in time domain astronomy than if we just evenly split the images across the entire footprint. In the recommendation PSTN 056, which we released in 2005, we had confirmed the recommendation to run the rolling strategy in 2 bands. You see 4 bands. There are 2 bands that get run simultaneously, but in different positions. And we also recommended not to start rolling immediately because we need to have a uniform enough survey in year 1 to calibrate the system, to cover the whole sky, to build templates. So we recommended not to start rolling in year 1 and to start it when we have achieved sufficient uniformity. And we have left that somewhat undefined. And then the other changes are observing in single exposures instead of 2 15-second exposures. We had recommended observing in 30 seconds. Single snaps, that single exposure, that has now been adopted. We have a number of sub surveys, which we'll describe in a second. And also we had specific recommendations for time allocations on mini surveys, such as the deep drilling fields, 7%, the target of opportunity, 3%. I'll go into some of those in a minute. But I want to show you this map. This is one of the ways in which the SCOC visualizes the performance of a simulation. So what you have on the y-axis are metrics that are mostly contributed by the community. So you write your math code that tells me how well you discover kilonovae, and now I can measure that against a set of simulations of LSST. Generally, older simulations are going to be put on your left side, and newer simulations are going to be put on your right side. And in particular, the one that I'm highlighting here is the one that the recommendation that we had made at the beginning of 2025, PSTN 056. What you red is worse compared to that. Blue is better than that. So what you would like to see is these maps to have a lot of red on your left side. That's the past. Those are simulations that we thought we were going to do earlier. And now we have the updated simulations, the new ideas, the innovation. So you would like to see that going bluer on the right. Specifically, everything is referred to a simulation, a recommendation. So you would like generally to see that that's the bluest one of all. And I want to emphasize that this map looks really well on that front. Most things are redder than our current recommendation, rather than being bluer than our current recommendation, with some exceptions. Notice that scale is 1.15 to 0.85. So those are relative improvements of up to 15%. And generally, we organize these. This is the most compact of the maps that we do. When we actually operationally work within the SCOC, we see hundreds of metrics that you've contributed. This map is as long as a sheet. But this is the succinct version that we generally post in our public communications. And it's organized by science groups, not super strictly, but generally. If you're interested in solar system, that's the top block. Galaxies are that block right there. Stars, time domain, which involves multiple science collaboration. And so it overlaps some of the other blocks. Cosmology, and then we have requirements for the system on parallax, proper motion, number of observations. So try to just generally keep in mind which region of the plot is your favorite one, because you will be able to then identify it in different heat maps like this one. So I think this is was a really important milestone to put out this recommendation in 2025. And we thought it was an extremely successful process to work with the community to design a survey strategy that has, over the years, massively improved on nearly all science goals of LSST. Thank you very much. Okay, a little bit more detail on what LSST means. LSST is a collection of surveys, and we run them with different strategies that are automatically set up by the brain of the operation, which is the automated scheduler. The footprint altogether that you see already includes some of the surveys. So the purple here is the wide, fast, deep. The green is the dusty plain, which is mostly of interest for Milky Way science. On the northern strip, on the top part, you have the North Ecliptic Spur, which is of interest to solar system science. And then you have the South Celestial Pole there. Those are mini surveys that are run concurrently for the entire LSST duration. We also have the deep drilling fields, which I was mentioning earlier. There are 5 pointings. You see them on that map. Generally speaking, the requirement for the deep drilling fields is to collect 10 times as many observations as the wide pass deep. The wide pass deep over 10 years will collect roughly 800 observations on each pointing, so 10 times as many, with some important details that I will glide over. Those are the position and the names of the fields. They were selected to be sort of legacy fields that already have large observation programs ongoing, multi-wavelength coverage, and of specific scientific interest. We have a specific and perhaps quite complex survey strategy for the deep drilling fields compared to what the original plan was, which was just to let's observe them a ton more. Over work that has been very closely in connection with the community, particularly the AGN community and the cosmology community that are primarily interested in these fields through a task force last year, we landed on this strategy, which we call the ocean strategy, because the ocean can be shallow and can be deep, or better, can be deep and ultra deep, because these are all deep drilling fields. So the requirement of the AGN, the primary requirement for the deep drilling fields of the AGN community, in addition to going deeper than wide fast deep, was continuity of observation. So extending the season to be a long season. You want to observe them as much as you can in time. Some other science cases, primarily cosmology, would like a more compact observing program that maybe shortens the season but gets a higher cadence. You do great with supernovae for them. So we were able to combine those two things, and our current strategy for the deep drilling fields is the ocean strategy, where we have all fields getting a deep season every year. So we observe them with 2 observations in G, 2 observations in I in even days, 2 observations in R and 2 in Z in odd days, and every few days in U and Y. That happens for all the fields for the entire 10 years of the survey, every year when the fields are visible. And the season length is about 220 days. But then we alternate each field to get an ultra deep season 1 of the 10 years. And the ultra deep season runs the deep season, and in addition collects series of 8U, 4G, 18R, 55I, 52Z, and 20Y visits in succession every few days. This is a highly customized solution that came from a very significant optimization over all the science cases. And this is our current recommendation for the deep drilling fields. We have a twilight microsurvey. A microsurvey is defined as something that takes roughly less than 1% of the LSST time. And we had issued a call for microsurvey in 23. We received a bunch of proposals. Obviously, we were at the time aware, we are still aware that the performance of the system is uncertain until the system runs and is stable. And so at that time, we evaluated the microsurveys on 2 criteria: scientific compellingness, I don't know if that's the word, how scientifically compelling they were, and whether they were urgent enough that we should devote some of the first year time, even though we don't really know how the system will perform in much detail, to that survey. And we identified the near-Earth objects twilight survey as the most compelling one on both fronts, particularly thinking of the rise of satellites that may interfere with performing this survey in later years. So this survey is currently running on LSST. And with the rise of the discovery of the first counterpart of gravitational waves in 2017, and with the existing gravitational wave programs, members of the community have strongly advocated and successfully advocated that we run a mode for LSST that is responsive rather than a discovery mode, where we follow detections of gravitational waves. That's the target of opportunity mode, which was not included in the original plan, but it has been approved and developed. The community contributions have been absolutely critical here, not only in advocating for the program to exist, but in designing the program, designing in detail how we should respond to not only gravitational waves, but also near asteroids and generally multi messengers or neutrino and gravitational wave triggers. So here you see a map of our response to simulated targets of opportunity. And but we not only have simulations, we actually have responded to target of opportunity. You've seen it yesterday. Sean McBride is writing a paper, has written a paper, which you now can find because it was submitted to SPI. We have a number of telegrams with our observations of the targets of opportunity. And I'm looking for Shreya. If Shreya's here, might not, but is presenting this at in different sessions. We also have a involvement. We have created a Rubin Target of Opportunity Advisory Board because this is a very recent and rapidly evolving field that can recommend on adjustments of the survey strategy as we have designed it for targets of opportunity, as well as on emerging scientific cases that we may not have considered to include in the target of opportunity response. And the survey strategy, the target of opportunity strategy is designed based on a report from a community workshop in 2024. And there's an updated community workshop report that is coming out very soon. So we will update the survey strategy accordingly. Okay. This is the past. And so I'm going to pause for a second and maybe ask if there is one or two questions. Most of the questions I would like to leave for the end. But any questions about the process of how we run the optimization of the survey strategy? Goes in 3, 2, Mario. All the way up there. Somebody has to run. And there's a competition because both Peter and Timo are trying to reach Mario. So, and Timo wins.
So thanks for that nice description. It seems like a lot of work.
It is.
The last couple of years, once we started surveying, we've discovered that the weather seems much worse than we thought it would be. Are your simulations now including kind of as experienced weather, or what are we doing with predicting what the weather is going to look like over the next 10 years, and how does that affect what you get here?
Yeah, I'm going to give a quick answer and then see if Peter wants to add anything. So we ran historical. Lynn.
I did look at this. The weather right now, we're probably heading into an El Nino year, and that is not reflected in our simulations. The weather last summer was actually, it's very hard to know exactly because we didn't have that long on sky, but the weather was actually reasonably consistent with our simulations for a it was just a normal year, not an El Nino year.
Thank
so
you.
I don't know if I agree with the comment the weather is much worse than in our simulations, except yes, this year it probably is worse, and we should change to a different year in our simulations.
We have a slide at the end that will address that specific point. Let me say just for a broader audience. So basically we run historical weather patterns. And the way we do that, we can change the start of LSST to hit those patterns a little bit differently. And that's how we make multiple simulations that give us some robustness to, or at least some measure of the uncertainty of the performance. Yes, my understanding as Lynn's is that it's not entirely obvious that the weather is substantially worse, not in a way that I can get anybody to tell me you should scale things this way. But, I share your concerns about global warming, so that remains a concern. One other question? Then, please, Richard.
Yeah, this relates to the deep drilling fields. Our lookup table is not perfect. So when we make a large slew, the image quality is degraded slightly. And it takes several images for the AOS to catch up. And so when we run the deep drilling fields, I see this all the time. We slew over here, we take 2 images and we come back. And those 2 images are just not as good a quality as they could be. And so I wonder if it would be better for the deep drilling fields to take more images at less frequently.
So in the ultra deep season, that's what we do. So I
Yeah,
guess your concern is for the deep season.
That looks good. It's the
which takes a
G2,
couple of
I2,
images.
R2,
So-
Z2 that I'm worried about.
I hear you. I don't know if anybody from AOS wants to help me answer, but the obvious answer is like, we have a budget. So, if we want persistent, continuous observation over a long season, we can only put a couple of observations in each filter there. So the budget is very highly constrained. So the optimization, venues to optimize it are limited. Anybody wants to speak about the AOS specifically?
I was okay. If there's an AOS team member there, they should answer.
No, Craig was clarifying his question. So I think you can answer if you want, Lynn.
So I was wondering if it was Craig's question.
Yeah.
Can't see who it was. Craig, is this still true with the current improvements in the AOS systems? Because I know it
Aaron
was
said it's
true
still true.
previously.
Aaron is saying it's still true.
I think we have not done the systematic study of that we could, but I think it's definitely still the case. Building lookup tables is something we could discuss at tomorrow's image quality session, but they are definitely not high fidelity currently, and building them has proven quite difficult. So, it's one of several different aspects of actual delivered performance that I think Craig is right. We're not taking that into account.
Yeah.
Obviously, inside the project, we've discussed this at different points over the last few months. I would say the other big issue of this sort, if I can add, is the wind direction. There's definitely evidence that certain directions are better than others, and that's that information is not currently being taken advantage of.
Yeah.
So go ahead, Lynn.
This is one of the places where I think we need to work together a little bit more with these summit teams, because I know that you are correct. Like there are analyses that are showing when the wind is at a certain level, depending on where we point, the scene can be better or worse. It's not clear if that is going to continue once we have more louvers. And I don't know the time scale exactly until we have more louvers. So I don't know exactly how to fold that back into the survey strategy. We do have the option to point to add masks and basis functions that help us point towards or away from the wind. It is harder to fold that back into simulations because we don't have the data to add it into the simulations at present. So I think these are really good points and really things that we need to look at more. And we need a little bit more coordination between some of the parts of our observatory to make this work even better.
And so the process would work like if we can assess what the image quality would be based on the survey strategy, we will go back to the community that has advocated for this survey strategy and see how to tweak it. We'll take one more question from online, and then we'll go to the next session of the presentation.
I just wanted, there's a back and forth on the Zoom about this particular question. So folks who are very interested should check out the Zoom chat, but I would mention that Saurabh asks, can we do something to optimize the wide, fast, deep or other observations before deep drilling field visits are closer, avoiding a big slew? So just maybe something for us to consider. And
Saurabh has chaired the task force on deep drilling fields. So he is the best person to come up with ideas on how to mitigate this concern. Thank you, Craig. Okay, I'm gonna move on. All right, so this is the heat map that I showed you earlier. Mostly red means it's good because everything is, generally speaking, most things are redder than our proposed baseline as of the beginning of 2025, which was the plan, but which was the proposal with which we were planning to start LSSD. What has changed since then, and what needs to change in the survey strategy as a consequence of those? of those items. So first of all, a better understanding of the system revealed that what we had built into the operation simulator as budget for engineering wasn't sufficient. We have probably going to require more engineering. The quantity is 10%. So that translates into, over the lifetime of the survey, we'll have 10% fewer visits, which is a significant number, which definitely impacts science. And then another significant change from that recommendation to now is that we knew this already. We need to build templates in year one. Templates are the images, the deep images that represent the static sky, so that when we take a new image on a night, if we want to do time domain astronomy, we can subtract that static sky image and reveal everything that changed. So if you want to discover supernova, that's how you would do that. So time domain astronomy relies on the existence of a template in each band across the entire footprint. And to build the template, we had assumed that based on the depth of the templates that we wanted, we were going to need 3 images, good quality images with decent PSF and transparency. And that understanding has been updated because what we had not taken into consideration correctly is the coverage that you had, so chip gaps and mask stars and all that. So 3 images will give you the depth, but the template will be spatially incomplete. So we're looking more at like 6 images per pointing. So we need to collect more images in year one to successfully build the templates of the sky. Those 2 changes drive our updated recommendation, which is PSTN 057, and you can find it here for how to start LSST. Now, this map looks bluer, but the bad thing is that blue is on your left. So the simulations that we have made before this recommendation were better. Well, we've lost 10% of the images. There's only, that's not really something that we can fix easily with survey strategy changes. So the simulation that the option that I was showing you earlier, the recommendation that I was showing you earlier is this one right here, circled in yellow. What we are recommending now is this one right here, circled in red. If we were running exactly this recommendation, including the template construction, but we didn't lose 10% of the visits, we will be here in this column that is still largely blue. So that shows you that the main impact that our science metrics are suffering definitely derives from 10% fewer visits. Generally speaking, the metrics in groups respond differently to this drop in number of visits. Things that depend on depth or number of epochs would fall like 10. Things that depend on number of epochs would fall linearly, so about 10% less science performance. Metrics that depend on co-added depth will fall a little bit less, 5%. Metrics that depend on cadence are the ones that are hit the hardest. And so this blue block that you see here, that is even saturated in this map, and this map is not 15% change, it's 20% change. This block is time domain astronomy. So time domain astronomy has taken the most significant hit because the cadence is sparser and we have fewer observations. One thing that I want to highlight is here all the way at the end, we have a hypothetical LSST that runs longer than 10 years. It runs for 11 years. And pretty trivially, you see that a lot of metrics recover because you get the 10% images back, but the ones that depend on the ones that depend on cadence, so the time domain metrics, many of them don't, because they still depend on cadence, and you can add observations, but you still have a sparse cadence, too sparse to allow time domain discovery and characterization. With that, I think that was my last slide. Lynn, is this you?
Yeah, this is where we said we'd hand over for a minute.
Thank you, Lynn.
Yeah, no worries. So Fed mentioned we lost 10% of our visits. I was going to, this slide explains where they went, basically. So the time we have available on Sky in all of the previous simulations was based on rather old predictions and information from the observatory like Summit and everything. However, we have now tried to get in better alignment with what is a more realistic schedule from planned maintenance, engineering time, and as well unplanned downtime. So the planned maintenance, we previously only had 2 weeks per year, which was a very small amount. So now we've gone to 3 weeks per year, plus 8 weeks on top of that in years 4 and 8. We now have planned engineering time, which we had none of previously. So we've put this in to the V5.3 simulations at 2 half nights per week for the first 6 months, and then 1 night every 25 days. Now, this is an approximation. It is because we have to have somewhere to start to put it into the simulation. We put it in as 2 half nights. This is likely to be a little bit variable. There could be some weeks that have 2 full nights. There could be some weeks that have only a few hours in several nights. This is probably not how it will actually look on Sky. And the other thing is, we actually, when we put this in, we had the understanding that weather would apply to engineering and to science. And we probably should have made engineering weather resistant, in other words, reschedule in bad weather. So the planned engineering time probably needs a little bit more in the first 6 months and maybe a little bit less in the 1 night every 25 days for the rest of the survey, because most of the time that 1 night every 25 days should be able to be done off Sky during bad weather nights. And we made no attempt to put those onto bad weather nights preferentially. So there's some uncertainty in there is what I'm saying. The unplanned downtime, so this is time that's lost due to faults or other unexpected things that take us off Sky. So we did have more unplanned downtime in the simulation starting at about 3.6. So at around the 3.6 simulation, we added more downtime in year 1. So previously we'd always had about 21 weeks of downtime in multi-night periods over the full 10 years. But at 3.6, we added more downtime in year 1, where we ramped from about 25% on Sky availability to 3%. But we did that over the course of 1 year. Now we're saying, okay, that was probably still optimistic. So that's it's not as bad. We've made it a little bit better, the on Sky time fraction. So we've gone now from 20% to 25%. But then we are only taking up to 5% and we're making that last longer. I think this is still something we're going to keep an eye on, like what's actually happening at the observatory, and then we'll update what we're seeing and update the simulations. But this is very hard to predict. And then the weather downtime. So like I said before, we use the same weather in V5.3 as we did in all of our previous simulations. The bad weather, if it happens at the same time as downtime, basically that just sort of covers the downtime. But it is clear that our default weather in the default simulation we run is probably not, at least for this first year, the real weather is likely to be worse than we have in the default simulation. We do run simulations with a variety of weather, what we call offsets. So we have weather records, cloud coverage records, basically, that run for over 50 years. And in different simulations, we can start at a different year in that cloud history. And what we do is when the clouds exceed 0.3 in the cloud history, we say, oh, that was bad weather and the observatory's closed in the simulation. So we use this cloud coverage records to make the observatory close or open in a way that should match the weather patterns on the sky. And we've checked this. Yes, we close more often at the right time of year. We've looked at the weather downtime, our model, compared to what we actually were off Sky last summer. It's a little difficult because we don't have all of the records about why we closed last summer. And we had some times when we were off the Sky essentially due to weather, but that we don't anticipate continuing, right? there's a lot of mitigations for coldness, the camera getting the system getting too cold, that have been made, that we won't have downtime for that in the future, but essentially that looked like weather last summer. So I do think there's things that we should look at with the weather downtime. I don't think it's clear that our weather downtime is incorrect in total. It's probably incorrect for the first year, and when you're looking at any shorter time period than the full 10 years, there's a level of randomness that can be hard to match. So it can look like it can look not consistent with what you're seeing on the sky. All right, can you go to the next slide?
Yes.
So as Fed was saying, with our normal survey strategy and the fact that we need more visits to build templates, we need more epics in particular, we found that we must intentionally take the images required to build templates. So when the seeing is good, when the cloud coverage is low, we need to spend that time building templates in parts of the sky where we don't have enough images yet for templates, instead of taking images for parts of the sky where we might want more I or Z, for example. So we have added we've added a survey mode so that we intentionally get templates, and this does influence the coverage in year one. But this commissioning did show us that without this, the likelihood of us not acquiring the images that we need to build templates is high, particularly in those bluer bands. Next slide. The other thing is, so the templates do need good transparency and good image quality, good PSF, but primarily what we see them needing from what we hear from data management is that it needs more epics. We need to cover the chip gaps, and we need more dithers and just more variety in the input images. So maybe we can gather epics faster by using 20-second images instead of 30-second images in GRZ. Why? And we would like to go down in U-band as well. We're working with data management and the summit, including the AOS teams, to evaluate the potential impacts or drawbacks for these. On-sky testing is going to be required before these changes can be approved and before we can check that it will actually work. Next slide. So some of the concerns, both of the SCSE and the community, include what will be the image quality at shorter exposure time, particularly in U-band. So U-band has the additional question that in U-band, we are very close to the readout limit. And as you make the exposure time shorter, we get even closer. And so when you're co-adding images, the read noise, the covariance of the read noise is different than the covariance of the sky. And so you can get different systematics with the co-ads. So that's something we'll have to look at. In all bands, it may be that the AOS doesn't converge efficiently when we have short exposures. So these are all tests that we have to run with actual data we get from on-sky. There may be some scientific impact on discovery with the lower depth in these images. It is true that most year one images are going towards building those templates. So if we did do shorter images, most of year one images would be shorter images. An alternative option is to consider delaying the construction of templates. So maybe we don't get enough images to construct templates in year one. Can we do it by the end of year two? This might be most relevant for U-band, which was already the band we had the fewest images in. Sorry, Fed put this last point on the slide. I'm not actually quite sure what you mean. Can you?
This idea of delaying the templates also relates to what you may have heard in other session about a proposal of defining year one, not by calendar, but by some scientific completeness metric. So if we did that, then the question of how long we have to collect templates changes, because the year one may extend beyond 365 days. So the construction of template will be thought about a little different.
Yeah, this is true. Yeah. Okay. Yeah. DR1 might not be just calendar year one. That makes, yeah, okay. Next
And
up.
on the right, I circled the simulation that includes the 20-second templates for people to see sort of like what we may regain in terms of metrics performance if we did that. So it's
Yeah,
generally better.
Yeah,
ahead.
although it's worth remembering that all of our metrics on the right-hand side here, these are all at year 10. So this doesn't reflect things like, well, we made the template faster, so we had more time on Sky while we had templates. Well, we had more images where we could use a template. And so our ability to detect these time domain events is actually even higher. And so it improves, but it might actually improve more because you got the templates sooner and could use the templates for more images.
Thank you. That's a very valid point.
Yeah. Okay, so as Fred said, there's not much we can do about losing the visits in terms of survey strategy, except that we can adapt the survey strategy by reducing what we're trying to do. So when the question is cadence, the answers are you could reduce your season length, or you could essentially increase the number of visits you have available at any point by reducing the amount of area you're trying to cover. So this is the task of the footprint task force. Can we regain cadence and depth by tweaking the footprint? The big hammer here is the wide fast deep area, because the wide fast deep area does get most of the visits for the whole survey. So this is just an example as a thing that we put together to say, okay, what if we reduce the area in the wide fast deep so that instead of covering area up to the dust extinction limit of 0.2 on the left, what if we just went up to 0.08? And so there's more, except for the galactic plane areas, galactic plane wide fast deep areas. So on the right, the area in the wide fast deep has gone down from 19,000 square degrees to 16,000 square degrees, but the number of images per point went up from about 650 to about 750. So the area on the right might be more useful for extragalactic science because it's much more concentrated into the low dust area. The galactic plane wide fast deep remains because there were different reasons for having that area. And so if we did this, you get more visits. This is back into our original range of number of visits we were expecting per point in wide fast deep. So likely the cadence and depth is returned as well. Exactly how to do this is an open question, which is why the footprint task force has been established. And Fed, did you want to make a statement about who to contact? You have the list of who's currently in the task force. And then
Right, we think we can add maybe a couple of people to the task force, and we're looking for people with expertise in science that for which the specific design of the footprint matters, of course. So if you want to join the task force, please just reach out to me directly. Best way is on Slack. I do have an email, much lower success rate in seeing your messages by email than on Slack. We just want to keep the limit to a couple of people just to make sure that the task force is small enough to still be agile and not have too many people that it becomes too hard to just meet and make collective decisions. We're not trying to be exclusionary in any way. And if we got 2 more people, we would have equal contribution from the survey cadence optimization committee and the community.
okay. Next. All right, and then the other thing we do need to talk about, and has been referred to many times in some of these different sessions, is there's a proposal to add early coverage, that is by the end of LSST year 5, of the northern part of the survey footprint in the wide fast deep area that overlaps with DESI 2. The request is to get 30 visits in UNG, 40 in RIZY by the end of year 5. The DESI request itself is actually being refined further to narrow down like exactly what is required. The 30 visits in UG, 40 in RIZ is what we understand and what we've run simulations with. Exact observing approaches, like can we tweak the rolling cadence so that it aligns a little bit better with the different stripes that people have requested? Can the area that DESI requested, which is about 5,000 square degrees, be split up into smaller chunks so that it has a little bit different impact on our cadence? The basic thing is, though, by requesting 30 visits in UNG by the end of year 5, on that table on the left, what you see is that by year 5, in baseline 5.3, we would not yet have gotten to 30 visits. So this does mean taking visits from later years in the parts of the DESI footprint and moving them earlier. And the earlier you move them in that plot to reach 30, the longer you have where you don't get visits, right? Because you were already ahead. You're only getting 45 visits total, in the baseline 5.3 simulation. So if you need 30 visits by the end of year 2, you have a long time to wait. You've used all those visits and you have a ways to wait until you get back to it. This is the same thing in a different plot kind of way. So this is a point in the DESI footprint. DESI 5 is our simulation where we split the DESI footprint up into 5 different bands. So there's 1,000 square degrees per year. I think it looks like it is in the top band, or so a band we covered by the end of year 2, maybe year 3. But what you can see is the purple and blue bands are UNG. So we get lots of visits in those bands early. So you got more early and then less late. So we spend a long time not getting visits and we had more visits early. The gain for Rubin is, besides like there could be potential gains with this survey strategy. Certainly it makes a wide variety of time intervals in some different parts of the footprint, right? But the DESI 2 proposal is that they would make available to Rubin about, excuse me, 250 dark hours on the DESI 2 instrument. There's a question. So, oh, sorry, but I have a frog in my throat, and somebody asked what is DESI and the expected gain from synergy with LSST. The expected gain is basically this paragraph on the right. DESI is a multi-object spectrograph that would, and it is a survey. So the idea is that by getting this deep coverage early, we have provided them the information so that they can pick targets for the DESI survey, DESI 2 survey.
Let me add that the DESI 2 survey is of cosmological interest. So for the community, for the LSST community that is interested in cosmology, that synergy is in and of itself valuable because it elevates the DESI 2 products.
Yes, sorry, that's yeah, obvious. Yes, obviously true there.
Sure.
As a separate, like, specific thing that comes back to Rubin is this proposal to make 250 dark hours available on the DESI 2 instrument. That these would be scheduled to target the deep drilling fields that are observable from DESI site. I'm sure we'll have more to talk about for DESI later, but let's talk a little bit just about, yeah, exactly. Exactly. There's some comments on the Zoom chat. Some thoughts on year 1. So Mario brought up the question, is our weather correct? Our weather is probably not right in the 5.3.5 or 5.3 simulations for year 1 in particular, because looking at ocean temperatures at present, looking at what we see with the weather doing so far, it looks very much like we're heading into a strong El Nino year. And our default weather year that we start the simulation in is not an El Nino year. It's not strong either way. It's just a generic year. So if I basically just add an El Nino year for year one of the survey, we do see a noticeable impact in the number of visits. The plot on the right is showing you number of visits over time for the first year of the survey, and the different lines are the same survey configuration, but starting in different weather years. So they all start on September 2026, but when we pull out of the weather, the cloud history, we pull from a different year. And you can see that when we start with the weather, and those on the right, 1982, 1997 are very strong El Nino years. 1987 is a moderate El Nino year. I know that 2015 was a very, very strong El Nino year, but we actually don't have very reliable records from that year. So I've not simulated that year. The last sim on there where it says 1997 and a visit gap scatter, this is just also trying to take into account the effect of some things about the actual visit gaps that we see at the summit. But you can see the primary impact is from the weather. This is about 25%. And this is before we throw in like, okay, what is uncertainty in engineering time or downtime? So this is the thing where we do have to take some caution about how literally we take the results of the simulations, and we will try to get them as good as we can, so we can make as accurate forecasts as we can. However, it is as you get to smaller and smaller timescales, like 1 year, it does get harder to predict like how many visits we'll actually get on the sky. Just because over 10 years, a lot of the uncertainty sort of washes out. Over 1 year, there's more left, right? As you can see here. So these are some simulations. I really just ran them over the weekend to look at like, okay, what happens when we take our simulation or configuration and we just run it with a different El Nino year for 1 year, and we can make these available. But yeah, this is where you start to say, okay, what are we going to have to do for when we're looking at what year one will be, what DR1 will look like, how do we evaluate what our templates will be, and this will feed back into the footprint discussion as well. All right, Fed, back to you.
Yeah, thank you, Lynn. I want to pause here. We have another section of this talk where we will tell you how you can monitor the progress of the survey in real time. Before we get to that, I want to take some questions about what we showed you now. And I see hands raised over there.
Okay. Just a quick question. When you're talking about the TVS metrics, and you were talking about the possible trade-off between high galactic latitude sky and low galactic latitude dusty sky, how do the metrics divide between extragalactic and galactic targets? And I imagine that will have an effect when one thinks about this.
Absolutely. So time domain science does include time domain science on the galactic plane and time domain science in the extragalactic sky. We have separate metrics for those. The metrics that, like I said, we have hundreds of metrics. Generally speaking, and the one that I showed you that are key metrics for TVS in the plots, the extragalactic metrics suffer more than the galactic metrics, but we do have TVS representation for both aspects of the science in the task force that could evaluate whether changing the footprint would reduce, worsen that balance. Thank you. Words.
So, in terms of the changing the footprint option, so that then gets the cadence, like recovers the cadence that you want for your time domain things. My question is basically around, like, I mean, just thinking through, you had the option where you run for an 11th year, recovers most, I understand that doesn't recover the time domain metrics because of the cadence. But my thought is, like, once you shrink the footprint, does your case for like going an 11th year to maybe recover other things get harder? I mean, is there, because then to recover the rest of the metrics, you'd have to only fill in on certain parts of the footprint. So that just seems like if you go that route, I guess I'm saying it seems like it would be then more difficult to later decide you wanted to, like, I think like once you do that, are you done? And then you can't really go back? That's my question.
So I don't know that that there is a solution on the footprint that would allow us to recover the metrics, the scientific metrics, and the requirement, the SRD metrics, enough to say, well, now we're good anyways. So it's very possible that the 11th year case continues to be relevant, or that the solution sort of sits in between. You don't reduce the footprint so much that you recover everything in Cadence, but you reduce it somewhat. I'm not going to speak to how compelling that case is to the audience of that case, because I don't speak for agencies. But it is also obviously true that once we decide on a footprint on the 11th year, we cannot do the rest of the footprint. So that is, yes, that is true.
Hi, thank you so much. This is an enormous amount of work, and you really appreciate it. So you asked a feedback from the science collaborations to improve your estimates, and we discussed among ourselves, and a very realistic vision of the year one will help a lot. So thank you very much for this kind of simulations, and if you can have it available for the science collaboration, will be extremely useful. This year, we also have the snowstorm. So usually this type of event can take, few months to recover the telescope at full functionality. Yep. So we will have to add these few months to the estimation for the worst, El Nino years. And that will have a very high impact on how we can visualize the R1 and how we can give you feedback. So I'm wondering if you can also add perhaps a simulation, sorry, that will estimate, considering the average parameters, only the observation in the summer, spring and summer, for example, where we could realistically think that some of the problems with this snowstorm will be, resolved. And then we can start to go in a routine, in the usual routine. And that will be really useful for proposals, because then we can convince the panels that even if there has been a snowstorm, even if we are in very strong El Nino years, we could observe something that will approximately, speaking about 50% of the time, and that will still be something exceptional with respect to previous survey.
So
in some areas.
Run the entire clock, right? Typically, we make the simulations from year 1 to year 10. Then the question is like, what do you run the metrics on? But the community is empowered to run the metric on subsets, temporal subsets of the, as well as spatial subsets of the simulation, right?
But so it's difficult for us because you see how much different
I can show you the line of code that you would need to do a query that only selects a subset of the months, and you can just run your regular metric, but add that query that would allow you to run it on whatever portion of it. Yeah.
Saying you will not change the cadence. If you would observe only spring and summer in year 1, you will not change the cadence.
Can I
Then go ahead.
Fred, I think the request is for let me see, tell me if what this is what you're asking. It sounds like what you're asking is, what if we didn't get back on Sky until the spring, and then what would we do? Could you run a simulation?
I'm asking, what if we go back on Sky only in the spring, and we can observe spring and summer, which are the best months, right? In that scenario, what would be the best cadence, and on which parameters the science collaboration can give an input to help you to optimize it for us?
My understanding
that was my
yes,
I'm sorry, I should explain.
I mean, we would need an actionable item for, I don't know what would be the best cadence if year 1 became 6 months, but Lynn maybe does, because Lynn wants
so this has not been part of the scope, right, of what we've been asked about. And my understanding is, even if we only had 6 months out of year 1 where we were expected to be on Sky, that at present, we would still expect to run the survey with the same general cadence and same general configuration that we would run for the full 10 years. That just because we only have 6 months, we don't say, okay, we're actually going to change things. The commissioning survey the SV survey last summer was a good example of, we actually knew we had a compressed time scale. We had a very small footprint. And even then, we were actually running a configuration that was very similar to the main survey. It's just because it was running on such a small footprint, the cadence ended up being higher from one night to the next. Yeah, this is a question I don't think we've considered. Like, if we only had 6 months to produce a data release that would be the most useful to the community, what would we do? And
I think that would be mostly a question for the community, right? So maybe we can turn it around. And if the community has thought that if we could only observe 6 months and you think we should make some significant changes, then bring them to us and we'll evaluate whether they're feasible, and then we would simulate them.
I don't know if I quite understand the question. If we didn't get back on Sky until spring, year one would start in the spring. And so the survey would then continue. So
yeah, I was going to chime in and say this kind of ties back to the what do we consider year one question of instead of a calendar year.
I do want to make sure that we have a little bit of time to show you how to monitor the survey strategy. So we'll take maybe one more question. I see John is, and he's in my department, so I have to like play favorites.
So it seems like the reducing the footprint, as we've already heard, means that you can never make it up, right? It's done, right? Whereas the time domain things, it seems like you're scaling sort of non-linearly, maybe, with what you lose, and you've have the committee, devoting 3% to TOO and 8% to deep drilling fields, which is basically time domain. And I wonder if the committee is considering whether scaling back some of those time domain programs to recover the metrics in the main survey while preserving, the full area, on the sky, is under consideration, or are you only considering shrinking the footprint?
The committee is considering everything, and so everything is under consideration. I think I pushed back on the deep drilling fields being only time domain. They're not. There's a lot of static science that depends on the deep drilling fields. And also I want to say that TOs are a very compelling scientific case that is already giving us results. So while not under consideration reducing that program, it is a very compelling program for the observatory altogether. So everything is under consideration, and we're looking at those things as well. But we're also looking at the footprint. Maybe you can take one super quick question online, just because I don't want to neglect the online audience. And Eric, do you want to come up in the meantime?
Yeah, I'll just acknowledge that there's quite a discussion happening on the Slack. And just as an overview, there's concerns about the DESI 2 taking up solar system and galactic science time that maybe doesn't benefit from DESI 2 as much. So please join the conversation online.
Yes. Thank you very much. Eric, do you want to tell us how we monitor the survey strategy?
Do I need a microphone? Okay, so we've been putting together some tools for, at this point, mostly seeing what did we do last night and how does it contribute to our survey. The first is a summary that comes in an RSS feed that is also sent to a Slack channel, so you can either use your favorite RSS reader or just subscribe to the Slack channel. It gives just very basic, that's not what I meant. Okay, it gives just very basic statistics on the night. Total number of visits, including things like engineering, science visits broken out by band, median PSF width, the total visit rate. So how many visits did we get that night? Total effective time over exposure time, which is a measure of how much you've contributed to the overall COAD. Note that 1.0 means a very, very good night, essentially pointing at zenith under ideal conditions all night. So you're only very rarely going to have effective time over total exposure time of 1.0. Effective time over total nighttime is the same thing, but instead of scaling by the exposure time, it's scaled by the total nighttime, so it takes overhead into account. And finally, there's a list of science targets. So what areas of sky did we do? You can quickly check this to see, for example, did we hit my favorite DDF field last night? At the top of that, there is a link to this. So this, the very top thing is a link. That link goes to a more complete report with a number of collapsed sections. So everything with a little arrow next to it can be unfolded into a more complete table of statistics on the night. And there are a number of figures on this table. I'm only going to talk about a couple of them here. This one is a map of the night.
Should be a video, but it doesn't look like it is.
Okay, it's a map of the night. You can hit the play button and watch a movie of what happens at night. It's in a couple of different projections. The left projection is an orthographic projection, and you can switch what view you have of it using the sliders on the bottom, and you can do it either in RA deck or as alt coordinates, depending on what you're interested in. There are also a handful of parameters for each exposure. You can just choose which one to plot as a function of time over the night. The infrastructure supports a much wider variety of things to plot here. If your favorite thing isn't plotted, let us know. We're trying to keep the total number of things that are offered under control, so you're not overwhelmed by them, but still have the most useful things, and we're open to input about exactly what should go in there. There's a DDF cadence plot. So when did we observe each DDF field, and how deep did we go, and what bands did we do? And so on any given night, you can see it's a stacked histogram. The height shows how deep it was, and the color shows what the band was. And so you can see for the most recent several months, when did we hit your favorite DDF field? And finally, you can look at a month cutout of the hourglass plot showing what reason the scheduler chose each field for. So you can see pairs, triplets, templates, whatever. And I think that's it for the progress monitoring.
We have another 7 minutes for questions, so let's keep the questions coming. And actually, let me acknowledge that largely a lot of these came from community asking for ways in which they could monitor the survey strategy, including that past meetings in this very session. So thank you for encouraging us to do that. And I hope that those tools are helpful. Can you give him the microphone?
Meg, can you try and see whether you can speak up?
Yeah, can you hear me?
Yes, we can.
Oh, great. So I guess the discussion or my plea on Slack was, we're all citing the Bianco 2021 Cadence paper, and that's V3, 3.5, I think. And so I think I want to urge really that and ask, whether the SCOC is going to have a cadence paper that we can all cite, right, about what the cadence is, or what is the starting cadence right now for LSST, one, to advertise, and two, so people aren't going back to that paper, because yes, there's tech notes, but they're not DOI'd, and sometimes people have had issues with journals on it, and I think it would be a strong shame if we don't have that. So I want to just make a plea. Is that possible, or ask, is it possible that we could get that, cadence paper to summarize what is the starting cadence of Rubin to advertise, but also help us as well?
Meg, the PSTNs should have DOIs. If they don't, it's an oversight. So they should be citable documents. That paper that you're mentioning, Bianco 20, whatever, is really describing the process of how we do the cadence optimization, not the cadence recommendation in and of itself. Those are in the PSTNs, but they are citable.
Well, it has 170 citations, so we're all using it to cite the cadence.
Well, if you want to talk about what the cadence is, that's not what you should cite at the cost of like removing some citations from a bibliography. Then you should cite one of the PSTNs.
I think the other thing that is maybe missing, at the first PSTN on cadence recommendations, we had a companion PSTN that like evaluated the simulations and the metrics in light of what went into the recommendation. And we sort of stopped doing that because it was very long and nobody looked at it. Nobody read it basically. It felt like it was a lot of work for something that was not actually very high return. But it sounds like perhaps what Meg is asking is, could you do that again with our current cadence as we're heading into the survey? That describes a little bit, not just like what's the recommendations and what the impact of them is, but like here's a simulation that's based on those recommendations and this is what we see.
We can do that. I don't know that that would be a scientific, I wouldn't know where necessarily to submit that paper, right? If it was a paper. So I suspect it will remain a technical document that is citable with an associated DOI. And I'll double check that all those documents have DOIs. Do we have more questions in the last 3 minutes? Oh, Agnes had a question about fleeted. Okay, well, if there are no more questions, thank you for being with us for the last hour and a half. I want to thank the SCOC, all of them, and especially the ones who made it here and ran the microphones and handled the Slack, Peter and Eric from the survey strategy team. And Lynn, thank you.